Yes. Okay. Okay, so welcome everyone. Thank you for joining for this Virtuaeolian seminar series. So we are very happy to continue this series of seminars with Dr. Nathan Brown today, and you can see on the on your screen the series that we have scheduled for the next months. So before we start, just a few reminders. So please keep your microphones off until we reach the question and answer section. You can during the talk ask questions in the chat, or wait until the end of Nathan's talk to ask the questions and speak aloud if you prefer. As you've noticed, this meeting is being recorded, and it will be shared later with the ISAR community for all of those who cannot attend the meeting. As you know, we are spread all over the world, so it's difficult to find a time that is handy for everyone. We ask everyone to contribute to creating and maintaining welcoming and respectful working environments that fosters diversity, inclusion, and belonging. And with this, I think this is all for the generalities. So now I will introduce Nathan Brown. So Nathan, you are assistant professor at the Department of Earth and Environmental Sciences at the University of Texas at Arlington. And there you have established a luminescence dating lab, and you have applied luminescence and other geochronology measurements to study geomorphology and active tectonics. And so today you are going to present us some nice work on the ventifact erosion in deserts, and we are very happy to looking forward to this interesting talk. Thank you, Nathan. It's the screen is yours, not the scene. The screen is yours now.
Okay, well, thank you very much, Philippe, and the organizers of this seminar for the invitation. I'm really happy to be talking about this research today because we're sort of at the midpoint of this project. It's a 3-year grant from the NSF, and we've started to get some initial results back, and so this is a really opportune moment to ask what we've learned so far. So today we're going to go to the deserts of Southern California and look at ventifacts and see if we can learn something quantitative about how they have been evolving. It's a very collaborative effort. I'll start with Jessica. So she was the first undergrad to join on this project, and she had a background as a professional photographer. And that came in quite handy because we ended up needing to do lots of photography of these ventifact boulders to create these detailed structure for motion models. And so she began that effort. And then Julia took that over. She was an undergrad in the lab, and then she was able to transform those photos into these nice 3D printed models. Let me see if I can do my pointer. There, you can see next to her, she's Velcroed these models to her poster board. So this is a great extension of our research into the outreach aspect of science. And then the majority of the data sets that you'll see today, Diana has produced. So she's been hard at work in our lab as well as lab out in Vermont, producing luminescence results and cosmogenic results. So this is really her talk. And then we have collaborators at other institutes. Nat Lifton is going to help us get some in situ radiocarbon erosion rate estimates from these boulders. That work is in progress. Paul and Lee at Vermont have been helping us with our cosmogenic beryllium-10 and aluminum-26. They run a really great visitor-friendly lab there. So if this type of stuff excites you, contact them because they are great collaborators. And then Julie Lady is really the one who taught me where to look for these ventifacts. And so I'd be lost in this project without her guidance. And then, of course, we always need field helpers. So these are 3 folks who helped us in punishing conditions. The topic today is ventifacts and ventifact formation. So simply, these are bedrock features that are shaped by Aeolian abrasion. They're not extremely common. If you weren't a geologist, you might spend your whole life without seeing them. But they're very intriguing features. They have these interesting shapes. And if you go to the more arid regions of the world, which the folks on this call spend their time doing, you'll likely see prominent ventifact features. Not only on our planet, with these high-resolution images coming from the Mars rover, we're learning just how prevalent these ventifacts are on planetary surfaces as well. And so learning more about their modes and rates of formation will help us understand how our planetary surface has evolved, as well as extraplanetary surfaces. There's a rich body of literature investigating the underlying physics responsible for ventifact formation. So, for example, on the left here is shown some analysis looking at how different sized sand grains of different compositions have dramatically different kinetic energy, or erosive power, if you want, depending on the wind speed at 1.2 meters. And then on the right-hand side is an example of a numerical study looking at how the material properties of the object being abraded, as well as the wind direction, can influence the evolving morphology of these features. And so we have many other examples beyond these. We have detailed expectations for how these things ought to evolve through time. But there's a basic problem, which is these rocks are often quite hard, and they're not eroding much on instrumental timescales. So it's difficult to figure out the abrasion rate beyond maybe a single sandstorm or two. Here's one study that I really like. This image was taken in 1952. So this is Bob Sharp, who is a professor at Caltech. And he's, in this image, setting up his field site that would last for decades. And so it's a little bit hard to see. Let me take my pointer. But he's got, for example, a natural rock here, and then he's put a metal strip over it to armor that region of the brick as sort of a reference point. But then he's also got some synthetic materials. So there are some lucite rods over here. He's got various polymers set up. There's a common brick right here. And he let those sit in the desert environment for a long period of time, and then made some observations after the fact. So I think this is just a really elegant study. We all know what the brick looked like before, and so then you can get an immediate sense of how much erosion happened. So on the upper right-hand side, this brick was set down 1952, and then he collected it in 1958, put this one in its place. And so that one sat there from 1958 to 1965. And then this brick down here, 1952, in the last 3 years of its exposure, it rotated around. So that was 1964. And then he finally brought it back in 1967. And you can see how dramatically that brick was eaten away by Aeolian abrasion. Here's another effort at quantifying erosion on instrumental timescales. So this study was in Antarctica, a couple sites, and they were using a micro erosion meter in this case. So the idea here is you just fasten this device, harness, I guess, to the boulder itself. And then you have this movable micrometer, and you can just push that little finger down until it touches the rock. And then you have a very precise estimate of how much the height has changed. They did this for 4 years. And at the end of that, they had this nice catalog of how much erosion on average had happened. And what you notice is that these two sites have broadly similar values. The x-axes are the same. And this magnitude, if you extrapolate that out to multiple years, is just difficult to measure unless you have these devices set up. And this is obviously something that has to be done well in advance, and these devices are expensive. It would be nice if we had a better way to do this, especially after the fact. If we could just go to one of these boulders, make some geochemical, geochronological measurements, and learn what the past erosion history might have been. And that's really the focus of this talk. So here I'm showing a recent paper from 2022 by Reza Sobadi and Christina Hippa, asking the question, can we use combined luminescence and cosmogenic radionuclide measurements to learn a detailed history of how erosion has evolved in hard rock surfaces? And so in this talk today, I'm going to investigate whether we can use those types of measurements to learn about ventifact formation. So here's the outline for the rest of the talk. I'll give you a brief overview of how these measurements work and how we can learn something about erosion rates from them. Then we'll go to the field and do some work. We'll come back to the lab, do some more work, look at the results, and then just a couple slides about what comes next and what we've learned so far. So the first question to ask is, well, how do these techniques actually work? Let's start with this ventifact sitting on the surface. We're going to be looking at the interior of the rock. We'll be sampling the outermost 5 centimeters at most, really. So as it stands today, we have some thickness of rock, but we want to move into the past when that rock was thicker, when there was stuff yet to be eroded. So as that rock sat on Earth's surface, it was being constantly bombarded by cosmic ray particles and by sunlight. And both of these influences produce interesting signals. So the cosmic radiation will create foreign nuclides within the rock. Beryllium-10, aluminum-26, and C14 are the ones that we'll be looking at today. And these are mostly created within the uppermost 60 centimeters or so. That's where most of the spallation profile happens. And with continued sunlight exposure, there is a latent luminescent signal within the bedrock that will bleach away, that will empty. And it empties progressively deeper with time. But the spatial scale here is very different. So with cosmogenics, if we're looking at maybe a 60 centimeter scale, with luminescence, we're looking at maybe a 2 centimeter scale. Very different scales. Now, what happens if we erode that rock down? Well, if so, then we're going to begin to remove the previous inventory of nuclides. So we'll strip away that rock that was rich in beryllium-10 or carbon-14. In the same way, we're going to begin removing that portion of the rock where the luminescence signal was bleached away. And so we will effectively be bringing that bleach depth closer to the surface. And the magnitude of this effect, how much of the nuclides we've removed, how close to the surface the bleaching profile is, the magnitude of these effects tell us something quantitative about the erosion rates. So that's the theoretical basis for our talk today. When we go into the field then, we're going to be measuring the very thin skin at the top to estimate the concentration of cosmogenic radionuclides and the outermost surface. And for luminescence dating, we're going to be taking a surface perpendicular core because we want to measure where is the signal bleached, and as we get deeper, where it becomes saturated again. We want to measure that whole profile. The fact that these processes operate on different spatial scales is useful to us. Because they're imprinting on different depths, they are sensitive to different length scales. And because of that, they're also sensitive to different time scales, because our erosion rate signal is really how much time does it take to remove those exposed portions of the rock. So this figure here is modified from that paper I showed you earlier. The averaging time scale, the time that this erosion rate pertains to, is very different for luminescence, or OSL, and for cosmogenics. Another aspect that I haven't yet told you about is these radionuclides decay at different rates. So something that is short-lived, like radiocarbon, will come into equilibrium sooner than something like beryllium-10. And so if you start looking at these lower erosion rates, you may start to sense several different time scales. And so this, we hope, will teach us something about whether the erosion rate has been constant through time or whether it has changed in the recent past. Here is a simple numerical experiment to demonstrate that we might be able to measure this thing. So in orange is an imaginary history where we have constant erosion rate with some noise, or in brown, there's no erosional noise. But that's been constant through time. If that were the case, then these techniques, luminescence or cosmogenic radiocarbon, should give us the same apparent erosion rate. By contrast, if you have a low background erosion rate, and then in the early Holocene, there's a spike in erosional activity, and then it returns to a low background, these different measurement techniques should give you different answers of the apparent erosion rate. Luminescence is only going to be feeling that recent low rate, whereas cosmogenics will be averaging over a time scale that includes both. And so it will tell you that the erosion rate has been higher over the time that it feels. So this is the basis. And now let's see how well this theory works. We'll go to the field first. So I called Julie Laney during COVID lockdown. I was wanting to go out into the field, but I didn't know where to go. So I said, I need to find a place that has ventifacts that are crystalline bedrock, because we want something that's difficult to measure with conventional techniques. It needs to be felsic enough that I can find quartz and feldspar, and I have to be able to drive there. She said, okay, well, here are two good sites to go to. So Garnet Hill is one, and here's Silver Lake. Silver Lake is about an hour and a half outside of Las Vegas. So Las Vegas would be over here. And it's a dry lake bed. This is the main sand source for this. And you have this volcanic edifice here. And at the base of these hills, you find lots of these ventifacts. Garnet Hill is right outside of Palm Springs, California. And you have the massive Whitewater River that's draining the San Bernardino Mountains, dumping out a huge sand supply here. And there's also this topographic funneling So you have the San Jacinto Mountains down here, the San Bernardino Mountains up here, and so the wind gets forced through this pinch point. So it's extremely high wind and abundant sand supply. And so on this hill, we find many ventifacts. These are the measurements that we're going to make on these ventifacts. The goal is to target 10 ventifacts in total. We'll make 3D models of their morphology. For each ventifact, we're going to collect one sample for cosmogenic radionuclide analysis. This is because it's expensive relative to what we're doing with luminescence, and it's relatively time-consuming. And so we're just going to be targeting the abrasion faces of these ventifacts. But with luminescence, it's relatively cheap. You can drill down into these rocks, wafer them, measure them on the instrument, and there's very little disposable cost. It's really just time. And so we're going to be ambitious here and collect 10 of these cores per ventifact. So a total of 100 measurements of luminescence erosion rates. And then we're also going to try and characterize these boulder surfaces. So when there are features like flutes, we'll measure their dimensions and their orientations. We're going to be estimating the hardness across the surfaces of these rocks to try and learn in a little bit more detail something about what erosion rate is responding to. So here we are, characterizing some of these ventifacts. Here's one shot where we've got our measuring tape down the face of this ventifact, and you can see the Schmidt hammer there, just doing a height transect to look at how hard this rock is. So the idea here is it's a concrete testing tool. So if you want to test the integrity of these pillars holding up bridges, you push your plunger in, and the plunger jumps into the surface, and then depending on how far back it bounces, if it bounces back very far, that's a hard surface. And if it hits the rock and just goes throop, then it's a very soft surface. So that's what we're doing many, many times. Then measuring the dimensions. Over here, she has her geologic compass, measuring the orientation of these flutes to see, are they aligned with modern day peak wind directions, or possibly where peak wind was during the Holocene. Another nice thing about these ventifacts is we're targeting larger boulders, and so we don't expect them to be moved around much during their lifetime. Measuring the depth of abrasion into these flutes. Here they're looking through a clinometer, and so we have to measure the angle of the horizon. And this lets us quantify what portion of the sky is blocked from incoming cosmic radiation. You can imagine if you're sitting within a steep valley, most of the sky is closed to you, and so you're only getting a small fraction of cosmic radiation. And so we have to look all around us at the height of the horizon. Next step, let's photograph these ventifacts. So I really like this image from this Verma and Burke paper. Cameras are readily available now, so this is even a little bit out of date. Now with our iPhones, we can do the LiDAR approach. But with simple photography, you can get very nice resolution 3D models of these surfaces that are also photorealistic. So here we are, we've placed, you can sort of see in this corner here, place some of these targets around so that after the fact, once we've stitched these photos together, we can spatially reference them and get absolute magnitude of our measurements. And then finally, we've got to collect these samples. And so we're doing a combination of drilling out these surfaces and also using a little angle grinder to extract some of these little brownie chunks. There you can see our water for cooling down our drill as we're going in. We're just using a paleomag drill here. sandy conditions. I had to go back to get some water. And on my way back to the field where Julia and Diana were working, I couldn't see them until the last 100 meters because it was very dusty that day. I'm a bad cinematographer, but it was the upside is you sort of learn, oh yeah, this is why ventifacts are forming here, because it gets very windy and dusty and sandy here. And you can see geology in action, which I thought was kind of neat. But makes for kind of gritty camping conditions, so not so good. Now let's go to the lab. This is the facility at Vermont. So this is a National Science Foundation supported facility where they train users to go through the entire workflow from just having crushed up rock all the way through to having fully purified targets of pure beryllium or aluminum that can be sent off to AMS spectrometers. So here's Diana at two different stages of sample preparation. Here you can see she's sending her sample through columns. The purpose of these columns, there's a little resin in there that you can sort of see like that. It's pulling out unwanted ions. One stage is for cations, another for anions, just progressively purifying her quartz. Over here, I think this is an HCl step, digesting away unwanted phases. And then later, we're going to be extracting C14. So Nat Lifton has a brand new C14 extraction line. So you're probably familiar with radiocarbon dating for organic material, but relatively recently, several labs have developed the capability to measure in situ cosmogenic radiocarbon with good efficiency. And so we're looking forward to getting those measurements as well, because those are sensitive to the sweet spot temporally where we can resolve Holocene effects. The other part of the project is luminescence. So here's the lab we have here in Texas. We use the same lighting that you'd find in like a film development lab. So you'll notice that the sunlight is bleaching away the signal at the rock surface. We don't want to alter that bleaching profile as we're preparing our samples. And so we keep very dim light and it's only orange. So UV is very effective at bleaching out, orange not so much. And our eyes have evolved to be sensitive to orange because we have an orange sun. Looks like this. We have these water-cooled drill presses, and we drill out these little cores, something like this. Then we have this handy little wafering saw. So this is used to slice up computer chips. That's the original intent, but we use them to get just over a millimeter thick rock discs. And so we go all the way down the core at that resolution. Those discs then get crushed up and we put them on discs and they get measured on our luminescence reader so that we measure the luminescence brightness of each wafer with depth so that we get the bleaching profile. And this is an empirical science and a very young science. And so one of the things that we're also doing in this project is trying to calibrate our measurements. So how does this bleaching profile evolve through time? Here we've created a fresh surface. So we've removed all the stuff that was bleached naturally. And then we let this surface beneath 2 centimeters. We shown the Mojave sun on this sample for 13 months. And then we came back and collected another. And then we went back later and collected another. And so we learn how, through time, this profile is getting deeper and deeper. And we're also going to be the erosion. So we've built these little devices where we can clamp our rock into this configuration here. There's a little stage that we can control how high up we raise the rock. And then we have just this angle grinder strapped on here. so we can progressively erode that rock as we raise it higher and higher. So the idea here is we're going to have rocks that are embedded within concrete. We'll erode them periodically, and then they'll live on the roof the rest of the time. So they're constantly exposed to sunlight, and every month or so we add some more erosion, measure how much we've eroded them, and at the end of about 18 months, we'll sample this and ask, when we know the right answer of how much erosion has actually happened, can we get the correct answer from a luminescence bleaching profile? So this will be one way that we can assign absolute erosion rates to our natural profiles. So, like I said at the start, we're a year and a half into it. We don't have most results yet, but we've got a few. And so I'll give you a little taster of what it might look like. The most impactful educationally, I think, result that we have would be our little structure from motion models. Here at our university, we have this makerspace, and I think lots of universities have these now where they're mostly student run. And for the cost of the little filament here, you can print out whatever you like. So you can make your little Dungeons and Dragons figurines that you paint, or you can make these ventifacts. This one, I think, cost $2 for me to print out. And I just love them. They're so cute. And they're really great for these meetings. So here you can see Julia has Velcroed them to her little poster. And so as she's telling people about these ventifacts, she can pop them off and say, well, see here, you've got the abrading face like this. So they're really cool. But they're also useful for more than just outreach. So we use these 3D models that we've created to contextualize the erosion rate measurements that we then make. So here you can see we're rotating around one of these ventifacts that we've got results for. We just looked at the downwind side, and now we're back looking at the side where most of that Aeolian abrasion was focused. So you can see this nice population of these erosional flutes across. You can see this ramp face that has developed. And what I'm going to show you now is our first set of luminescence erosion rate measurements. These aren't yet absolute values. I can't give you anything in millimeters per year, but I can show you relative differences. So these are uncalibrated, but we can learn a few things anyways. I'll tell you what you're looking at here. The deeper red colors are higher relative erosion rates, and the whiter colors are lower relative erosion rates. In other words, the intense red means the profile is close to the surface. There's been lots of erosion to remove the bleached bits. And then the marker shapes tell you something about the placement of these erosion rates. So we've got two on the downwind side. We'll call that the non-abrasive face. One there, one there. These circles tell you we've sampled on the abrasive face, but not within a flute. And then these diamonds are taken from within these flutes themselves. So if this talk were honest, I would have told you that I didn't care so much about ventifacts from the start of this project, but to hammer everything is a nail. And so we had this really cool new capability with luminescence dating where we can measure erosion on such small scales. And so I thought, well, what is something where you have erosion happening on this really small scale? And ventifacts were the answer to that. Now, after the fact, it turns out that they're very cool, and now I do like them for their own sake. But the ability to measure erosion on such a small time scale, time scale and spatial scale, is what drew me to this project. And so here you can see that we've got an erosion rate measurement within and outside of this flute. Now, at this point, you've probably made your own judgment about what's going on here. But here's what I see. We see the opposite of what we would expect if these things were actively forming today. Down here, we have the lowest erosion rate of the whole group inside this flute and the highest erosion rate outside of the flute. So this is, again, the opposite of what we would predict. Up here, this is sort of the null hypothesis case. These erosion rates are indistinguishable inside the flute and outside the flute and inside that flute. The other thing that we don't see is we don't see a strong height gradient. So it's not the case that we've got really high abrasion rates up here and they get lower as we get closer to the ground and the velocity of these impacting sand grains is getting lower. So I think overall, we can conclude that these things aren't forming very much today. We made these hardness measurements, so I wanted to add this for a little bit more context. If you measure the hardness within these flutes and outside of the flutes, so outside and inside the flutes, there's not much systematic difference. The rock seems to be equally hard. If you measure the non-abrasive face, the rock seems to be a bit softer. I interpret this as maybe a weathering artifact. This sort of varnished surface is maybe more intensely weathered, less fresh than the abrading face. But maybe you have more insightful observations here that I'd be interested in hearing. But either way, I think we can say that at least for this ventifact, there doesn't seem to be a systematic difference within and outside of flutes. And there doesn't seem to be the expected trend of a height-dependent erosion rate if this thing were actively eroding today. So maybe it's not. And when I say today, with luminescence, that kind of means on annual, decadal, or maybe even, if it's low enough, centennial timescales. So probably just background erosion rates on those timescales. Okay, now we're going to zoom in and I'm going to show you something about topographic shielding. So Diana and I yesterday were trying to speed this video up and then we realized we had to get too deep into Excel to do that. And so I said, I'll just filibuster while this is happening and maybe no one will notice. So here we are getting closer. We're almost there now. And we did it. So these 3D models are useful scientifically because they let us do another thing. They let us calculate how the rock is shielding itself from cosmic radiation. This is one of the tricky things about irregularly shaped objects. A nice flat bedrock like this, all the incoming radiation reaches your sample and there's no complication. But if you get these angular features, sometimes the rock is in its own way and it's blocking that radiation, like this. So this is some computer code that Greg Balco wrote, and it lets you model how each of these incoming cosmic rays will either meet your sample without much attenuation, or maybe it's coming at a low angle and it travels through some of the rock before it eventually finds your sample collection spot. So this is a necessary calculation for these oddly shaped objects, and this photogrammetry allows us to approach that problem. Now I'm going to show you the cosmogenic results that we have so far. We only have one nuclide measured so far. We've got our aluminum-26. Any day now, we're expecting our beryllium-10, and cosmogenics will probably take, or C14 will probably take another little bit. Here's our aluminum-26. And I'm going to show you in two flavors. With any cosmogenic exposure measurement, you can cast them as an apparent erosion rate or as an exposure age. So I'll show you both. We have 4 ventifacts at the Silver Lake site. These two were collected near each other, so we were really happy when they gave similar results. This one up here had dirty quartz, so we couldn't get a measurable aluminum signal there. And the one over here is giving us a rate about the third of these. So these numbers are reasonable numbers. These are numbers that the literature would tell you would be realistic for crystalline bedrock. And then here are the apparent exposure ages. These are the effective ages of these boulders. So we have about 25,000 years and 65,000 years. Now let's go over to our Garnet Hill site. Here we have 6 different measurements. So we have a little bit more spatial resolution. And you see some variability spatially. They're all within an order of magnitude. But when we first plotted these up, we were sort of thinking, I wonder if this is related actually to position in the landscape. And so we drew these really crude sort of iso lines, these iso erosion rate or isochron ages. And so actually I want to jump over to, oh, no, I'll show you this first one. Here's some context. This is that slide I showed you earlier from that Antarctica study. These were measured erosion rates over 4 years, and they're in units of millimeters per year. So multiply by 1,000, and you've got something ranging from, I don't know, maybe 5 to 40. And then you look at our rates, yeah, they're within that ballpark range. So these aren't crazy numbers, I think is the point there. But now let's look at ages. You can see that there are these 3 domains. Near the tops of these hills, we have apparent ages of about 100,000 years. And then within these 2 little draws, we're looking at maybe 60,000 years. Over here, maybe 78,000 years. These are older ages than I was expecting. I think what we've learned so far is that these boulders have a long life on the hillsides. The Holocene, if there was peak Holocene erosion, which is what some people think, that erosion wasn't enough to entirely erase the inherited cosmogenic nuclide signal. They have a memory of earlier time periods. This places constraints on how much erosion can have happened in the Holocene. Okay, 2 more slides and then I'm done. Future work. This was a figure from the proposal. This is what we're going to try and do once we've got all of our results in. We're going to try and correlate with wind direction, see whether with some of these ventifacts we have systematic trends of erosion rate with height, inside and outside of flutes. We're going to be looking across time at how these cosmogenic and luminescence-based erosion rates are evolving, and then ask if we have relationship with hardness. On the ventifact that I showed you earlier, not so clear that we do. But stay tuned. If you see me in 2 years, ask me how it went. What conclusions can we make so far? Structure from motion photogrammetry is a great, cheap tool for characterizing surfaces like this, both for research purposes and public outreach. The initial luminescence results that we have suggest that at least the ventifact I showed you and one that I didn't show you don't seem to be actively forming today. This is consistent with the idea that some have for Southern California deserts, that maybe peak ventifact erosion was happening in the early Holocene, and it has decreased substantially since then. The cosmogenic aluminum-26 results indicate that these boulders have sat on the hill slopes for 20 to 100,000 years at least without overwhelming erosion. So recent erosion was not sufficient to completely erase inheritance. But it's going to be really interesting when we get our carbon-14 results, especially because these are sensitive to a very different time scale. And the ratio of C14 to beryllium-10 to aluminum-26 may give us some power to learn whether or not there was elevated erosion in the Holocene. Okay, and with that, I'm happy to take questions. Thank you for your attention.
Thank you, Nathan. That was a very nice, very interesting talk. So now we have some good time for questions. So please either raise your hand or put something in the chat, and we can gather questions. I have a few questions myself, but I'd like the audience to start. So who has the questions? Don't be shy. Maybe I can start with a question meant to show the good example. So maybe this is a naive question to start with. So what is the difference between ventifacts and yardangs? Or in other words, can you apply your technique to systems like yardangs? Maybe they are more active today. Can you measure something, and what can you make a bit of the comparison of the two?
Yeah, I think so. The nice thing for my technique about ventifacts is we want to be able to extract an intact column of rock that we can make these measurements on. If it's less consolidated, so if you have this landscape-wide erosional landscape, if you can measure a depth-dependent signal, then I could estimate something about erosion rates. But if it's less consolidated, then I really can't. You could do cosmogenics for sure, but with luminescence, having bedrock to measure is critical. So that's why we've targeted these in particular.
Okay, thank you. I can see questions by JB in the chat. Maybe you can.
Oh, sure.
I
You assume constant conditions over very long time scales. What would be the role of temperature changes, rain, ice? Yeah, okay. So the hope is that we would be able to resolve whether or not there were constant conditions through time. So if we get the same apparent erosion rate for all four types of measurements that we're making, luminescence, C14, beryllium 10, aluminum 26, then we can say it seems like there have been that something averaged over hundreds of years and tens of thousands and 70,000 years. If these numbers are the same, maybe it is constant. And if they're different, then I think, which I'm sort of expecting they might be, then I think we would want to appeal to the sorts of things that you're describing, JB. Because yes, I mean, these environments are very dynamic, and probably there are periods when it's elevated. And so I'm hoping that we can pull that out with the measurements.
Okay, Cheryl has a question.
Yes, hi. Really
Hi.
great talk, Nathan. I really enjoyed it, and I think I love ventifacts as much as you. Most of us
cool.
do. Yeah. My first experience was seeing him in the Arctic under extremely cold conditions, and it's nice to see a warm temperature environment example here. The digital elevation models that you've collected through structure and motion, those are a fantastic resource, and I was just wondering if you might be considering sometime down the road making a library that might be publicly available for other researchers to access. And specifically, for my framework, we've done a little bit of work on ventifacts from the dry valleys in Antarctica, looking at the fine scale ornamentation, and we stick them in the wind tunnel here and we blast them with sand, and we look at feedback between the form, the siltation cloud, and the airflow. And I'm looking at some of those spindle shape scallop forms and the flutes, sorry, early morning here. Anyway, and thinking, wow, it'd be great to have access to that so that we might be able to kind of extend our analyses to look at some of those forms. Is that, I guess it's a comment and a request at the same time, but would you be willing to do that sometime down the road?
Oh yeah, I'm so happy that you asked this question, because yes, this is a stated goal of our proposal, is we want to push these out to the community. So what we're aiming to do is put up both the like 3D print files so that you can go out and print your own for a couple bucks, and also these 3D photorealistic spatially referenced models. So there are all sorts of sites these days, like Thingiverse, and I forget the others, where you can just upload. So we're going to do that. We'll put them out to these freely available websites. We're also hoping to make sort of like compiled educational modules where we have a video saying, hey, go to this site and notice these erosional features, and here's where you can go to print them out for yourself so you can play with them. And actually, if you put your email in the chat, we've got funds to like send out some of these objects free of charge on a limited basis. So if you send me your email, and I'll get your mailing address, and I can send you 10 of these little things for your very own.
Okay. That'd be fantastic. Thanks, Nathan. Full disclosure, I have an honors thesis student trying that wants to undertake this for next year, so the timing would be perfect. Yeah, I said, well, I'm sure I can find a ventifact somewhere, so this is this would be fantastic.
Oh, very exciting.
Yeah,
oh,
thank
cool.
you. So I'll put it in the chat,
you.
and then we'll keep the conversation going. Thank you.
Awesome. Yeah, thank you.
Other questions by someone else? I have another one, a quick one. So you for the flute, so you mentioned that you measure the same erosion rate, within the flute and on the and next to it. So what is the formation process than you expect then, or are you just saying that it should be formed as we expect with more, but then it's I don't understand why, if we still see the flute, then suppose that this was active in the past, and then not active for I don't know, for centuries, for for whatever. And then why would this erode uniformly and maintain this shape? And so saying that it's not active now, it looks like a bit of a contradiction to me.
I see. Yeah, that's a great question. So one possibility would be, so when this flute is doing most of its formation, you would expect in that moment, if you made the measurement, that at the bottom you would have a shallower bleaching profile. You'd be able to measure the erosional difference. But my interpretation is that happened, say, 8,000 years ago, was peak formation. And since then, maybe it's been sitting, kind of keeping its same shape. If it keeps its own shape for 100 years, the luminescence profiles will adjust back to some background level, and they'll be indistinguishable from each other. That's my interpretation of what's happening there. So not necessarily that that there's a lot of ongoing erosion that is keeping pace in the bottom and the top, but rather erosion has effectively ceased since then, and the profiles are just evolving back into some background state. So I think it places a limit on the maximum amount of erosion that could be happening today, but it doesn't tell us much about what erosion looked like when those things were actively forming, is my interpretation of that.
I understand. Okay. Yeah. Thank you. Okay. One last questions. What did you say? Oh,
JB was impressed by all the sand inside the tent.
okay.
Yes. Yes.
Okay. No more questions. Okay. So thank you very much for all the people who are attending this talk. So please remember, and you see this on the screen. Do register for the next meeting. Exactly in a month, Colin Marvin will speak about Aeolian sand microtextures. And then in June, Yaping Shao will present his work in recognition of his ISA Career Award this year. And then in July, Chloé Dodon will present some work on Barkhan migration. Please register, put these dates into your agenda and participate. Thank you again, Nathan. That was a great presentation. Thank you, everyone, and hope to see you later for the next talks. Bye-bye.
Okay, thank you.